Okay, வணக்கம்ப்பா. குட் மார்னிங். வணக்கம். ஸ்ரீவர்ஷினி இஸ் ஆன் த லைன். வணக்கம்மா.
வணக்கம் சார்.
வணக்கம் வணக்கம். ஸோ டெஸ்ட்லாம் முடிஞ்சது. ஸோ வில் ஸ்டார்ட் ஆஃப்டர் that. We are going to start new topic today. ஓகே, டெஸ்ட்லாம் எப்படி போச்சுமா உங்களுக்குலாம்? பரவாயில்லையா? எல்லா டெஸ்ட்டும் முடிஞ்சதுல? ரைட்ப்பா, வைத்தீஷ். வேற கெமிஸ்ட்ரி டெஸ்ட்லாம் எப்படிப்பா போச்சு? அவங்கெல்லாம் எப்படி எம்சிக்யூ ப்ளஸ் ரிட்டன் ரெண்டுமே இருக்கா? வைத்தீஷ்?
எஸ் சார், ரெண்டுமே.
எவ்வளோ வெயிட்டேஜ் போட்டாங்க, ஏதாவது சொன்னாங்களா? சரி, ஓகே. நான் இப்போதான் கரெக்ட் பண்ண ஆரம்பிச்சிருக்கிறேன். பார்க்கலாம், இன்னும் 2-3 நாளில் சொல்லலாம் அதை எப்படி பண்ணலான்னு. சரி, ஓகே. டெஸ்டோட ஃபீட்பேக்லாம் அப்புறம் கேட்டுக்கலாம். ஸ்டார்ட் திஸ் நியூ யூனிட். டுடே வாட் வி ஆர் கோயிங் டு ஸ்டார்ட் இஸ் நைஸ் இன்ட்ரெஸ்டிங் டாபிக். வாட் இஸ் கால்ட் ஹீட் ட்ரான்ஸ்ஃபர். முதல்ல இதெல்லாம் க்ளோஸ் பண்ணிடலாம். What is it? How to do this? Okay, Paha. Welcome you all. We are now going to third unit. Of course, we are yet to see one small aspect in this second unit, which is about cavitation and water hammer. That we will see. After about a week time, we will see that topic. Once we are done with this paper correction, we will see that. Maybe in the week kadisla, otherwise next week la paakalam. Okay, we are again to say we are from the campus. We are we are working from campus. On all the 6 days, we will be in campus. Another topic, today we will see the nice, interesting topic of chemical engineering, which is heat transfer, which is very, very, very easy to understand as well. Out of all chemical engineering core subjects, this subject, which is heat transfer, is the easiest subject. Of course, we can easily even experience this heat transfer. Otherwise, how do you experience? Otherwise, you can very well feel the temperature of any object easily. Simply by touching with your hand itself, you can see whether it's hotter or colder. No. And the direction of heat transfer always from higher to low temperature. So that is by experience we have come across this, and we can easily understand this subject in a relatively easy manner. 1 minute, it is going out. Yeah, right. The syllabus given is, of course, we are splitting into some 2-3 topics. One is about the basic principles of heat transfer, which is conduction, convection, and radiation. And also let us see the total syllabus so that we can syllabus of this full heat transfer topic. So if you see the heat transfer syllabus, heat transfer, conduction, convection, this will finish it today. And another is about flow arrangements in heat exchangers, which is giving idea about temperature variation, or what is called as temperature profile of the fluids which are exchanging the heat. And next is about the heat transfer equipment, simply called as heat exchangers. And another topic is about evaporators. So evaporator is also a kind of heat exchanger, but the purpose of this evaporator is mainly to concentrate a liquid solution. So otherwise, we are having these contents in 4 major broad categories. One is the principles of heat transfer, which is conduction, convection, radiation. And second is about the temperature profile or variation of fluid temperature in heat exchangers. And another is about heat transfer equipment, some constructional aspects. of this major equipment, which is called as a cell and tube heat exchanger. And the another aspect is evaporators. So these four topics we'll try to finish it in so there are 2 weeks time, this week and next week. Sardanapa? Okay, the other aspects we'll see. And for this heat transfer, I have also prepared this. What is it? In the last year itself, I have prepared this recorded lectures. Otherwise, without any students, otherwise it's kind of pre-recorded lecture. That lectures also I will make it available by this in another about half an hour or so. In another about 1 hour or so. So that recordings also you can go through. So otherwise, for from next class onwards, we can discuss based on the pre-recorded lectures. So otherwise, I need not elaborate every aspect here. I will ask you to go through these videos, and for the coming class, I'll make a discussion based on the class this video contents. Otherwise, you also need to have a preparation for the class. Okay. Prepare but you can easily understand that contents. That's why this you can easily come prepared for the class, next classes. Coming to the today's content, which is heat transfer, conduction, convection, radiation. We are going to see the various modes of heat transfer. These types of heat transfer are also called as modes of heat transfer: conduction, convection, and radiation. Of course, sometimes all these modes of heat transfer will prevail together, but we can also study them separately. Otherwise, the radiation will normally associate to happen only whenever the temperatures are very higher. Otherwise, the relative contribution of the radiation will be much better whenever the temperature differences are higher. And convection, whenever there is a motion of fluids, and conduction, what is happening through a solid. But in reality, this during convection, conduction will be there, and also radiation will be there. But we will study the subjects topics separately, and we can also solve the problem combinedly. That combined solution and all you will see in your heat transfer course. Okay, see, we can easily understand this heat transfer by the way of this slide. So we are heating some wooden. There is a fire, and whatever you see by touching with the service, some steel rod or any other conducting material. So the heat is traveling through this material by conduction, whereas you can also experience heat without any solid object, or directly keep your hands over that fire. Whatever the heat coming to is coming because of convection, or is convection is coming because of flow of the fluid. Here the fluid is nothing but your this fire as well as the flue gases. And radiation is happening because of what is called as electromagnetic waves. And we'll also see this radiation is happening with radiation doesn't require any medium for heat to travel. There is no need to have any medium at all. Otherwise, say the sun's radiation is reaching this earth by radiation, what is called as electromagnetic waves or quantum wave. So there are a lot of theories available, but it's traveling through vacuum. Of course, the atmosphere is there only for a height of about 10 kilometers. More than beyond that, people say some ions or ionic layer, something is available, but predominantly it is kind of a vacuum is available. So in that vacuum, the sun's rays are reaching because of there is a phenomenon which is called as electromagnetic waves. So this phenomenon and there is physics or this minute aspects and all we won't study. Whereas we are going to see how this subject as such is going to used to study the transfer of heat from one fluid to the other. Then the application of simply say the application of this subject is to understand the heat transfer happening in heat exchangers. Heat exchangers you have already come across. Say in the case of your laboratory preparation of some chemical, say you have taken the chemical in a round bottom flask and you are heating that by the way of a Bunsen burner or some electrical heating. So heat is transferred to the contents by the way of conduction as well as radiation. Then what is happening inside the round bottom flask is nothing but the convection, and it may also lead to boiling. Convection, what is called as convection with phase change. So boiling, and also whatever the boiled contents you'll be getting some vapor that you'll try to remove the heat of the vapors using putting some condensers surrounding the this vapor. So in the condenser you'll be circulating cooling water. Yeah. So always most of our chemical engineering operations are involving cooling or heating or say maintaining the temperature at the required temperature. So for that we'll be having heating, cooling in large amounts. So for that we need to study these modes of heat transfer. Okay, this is another illustration. The same thing, of course, kettle. So we can see this conduction in this what is it, handle, and what is happening, what is how the heat is going from the flame to the material inside the container is because of the conduction, and even the radiation can also supply necessary heat. Radiation normally happening at high temperature of the order of about significance will be much higher only at high temperatures. And what is happening inside the kettle is convective currents. It may be involving boiling and condensation. So always all the modes are happening simultaneously. But for study, we'll see the conditions under which each and every mode is in separate or is predominantly occurring. Like conduction will happen whenever you have only a solid phase or a stagnant liquid. Stagnant liquid, not only liquid, stagnant fluid. So, okay, we'll see the thing. Conduction is the transfer, heat transfer due to temperature gradient. Of course, any heat transfer is due to temperature gradient. Convection because of the fluid which is carrying the heat. And radiation is happening at all temperature above absolute zero temperature. So, otherwise, any material is capable of radiating whenever its temperature is higher than 0 Kelvin. That means naturally every material is radiating. And radiation exchange depends on the temperature difference available. Okay. So radiation as such refers to the emission of heat energy, and it is happening at temperatures, any temperature above absolute zero. Or is practically at all temperatures, radiation is happening. Say this another schematic which is about conduction. Whenever there is a temperature difference between the solid, say whenever there is a temperature difference between a stagnant solid or a stationary fluid. Stationary fluid means there is no movement, bulk movement of fluids. Maybe the energy can exchange because of the molecules movement or what is it, some atomic movement, but there is no visible bulk movement of fluid. In that case, this conduction is happening, and we can even draw this profile, what is called as temperature variation with reference to the distance. So you can see this T1 this side of this material is at T1 and this side of the material is at T2. Assume T1 is higher than T2. So hope my mouse movements are visible. No, so I am referring to the picture in the left one. Screen sharing. Yeah, suppose our screen sharing. Okay, screen is shared. So Q, the small q refers to heat flux. Heat flux means rate of heat transfer per unit area. So otherwise it is having the units of watt per meter square. So what is the rate of heat flow? Otherwise joules per second. And divide by the flow area. Heat transfer area is a area perpendicular to the this heat flow. See this temperature profile. This temperature profile is there because of the this what is it conductivity of the material. So otherwise, for solids, we will have a property what is called as thermal conductivity. And for fluids, this is about the convection. Here, this okay. Assume the solid is at a temperature of Ts, and nearby you have a fluid moving, which is moving because of a forced flow, or the fluid can also move because of the temperature difference available. Say the solid is available, assume the solid is available at a higher temperature and fluid is at a lower temperature. What will happen? So whatever the fluids which are all in coming in contact with the solid will be getting heated up, and that will lead to uh, creating a density difference. So whenever the temperature is increasing, its density of the material are normally decreasing. Correct, Sanapa? You would have seen that, no? This density of the material is decreasing. So that leads to low density material, and over which a high density material is available. Why it is high density? Because of low temperature. So that high density material will try to come down because of the gravity. So there is a motion of fluid created, which is arising because of the temperature difference. So otherwise, the fluid flow can be forced by a pump or a fan, or a blower, or the motion is created naturally because of the temperature difference available. So the temperature difference is creating a density difference. So the density difference will definitely lead to circulations. Patrick, you would have seen this kind of flow creation. As and when you take some contents and try to heat the contents. So what will happen? This fluids closer to the solid body will be at high temperature. So they will be of low density. So they try to move up because of otherwise high density fluid is coming down. So there is a circulation created, and this circulation will be very vigorous during this condition of boiling, because in the boiling conditions we'll be having this liquid is turning to vapor. So this vapor and liquids are of very high density difference. Now vapor is having a density of roughly about 1 kg per meter cube, and that of liquid is about 1000 kg per meter cube. So this 1000 times density difference creating very fast movement of this vapor, is what is called as vapor in the form of bubbles. So that's why this during this boiling situation, we will be having a very vigorous heat transfer happening. Otherwise, uh, motion of the fluid is very vigorous, very enormous. Though we don't move the fluid by any forced means, or otherwise you can also move the fluid by using a pump or a blower. But normally in our household applications, this flow is created because of these boiling situations. There is the condition happening in this process: convection with phase change. Convection may happen without phase change and with phase change. So there is convection without phase change, simply what is it, the heating up of a liquid or heating up of a gas, whereas with phase change is the boiling and condensation. The reverse of boiling is condensation. So these are all topics of discussion in convection. Okay, this convection in detail you will be studying in your heat transfer course. And in your fourth semester itself, you will have this course. This convection you will study in two units: convection without phase change and convection with phase change. This convection with phase change means involving condensation and boiling. And likewise, conduction you'll be studying in a whole semester. Sorry, whole unit, one chapter, and like that, radiation also you'll study in one chapter. So otherwise, this convection you'll be studying in some two units, and this and again about heat transfer equipments. So otherwise, which is having all these heat transfer modes happening in a single equipment, is what is called as heat exchangers. That you will study as a separate unit. Or is these three unit modes are happening in a heat exchanger. So this heat exchanger is a separate unit. Conduction, convection in 2 units, and radiation 1 unit. So all of them. So this is a whole semester, or is one semester subject as such. Okay. Okay, this coming to the conduction, always we are now going to see each and every modes separately. And also again to tell you this, we are going to see simple equations without involving much derivation. And also we won't see any problem solving. Always we will see simply the applications. So conduction is due to the random molecular motion. Always in the solid, how the energy is getting transferred from one molecule to other molecule or one atom to other atom. This is happening because of what is called as the motion of free electrons. And in the case of fluids, the molecular motions. Okay, it's not to worry much about how this is happening in the material. So we'll directly go to the equation as applicable. Yeah, of course, here now we'll see the variables. The small q, already I have said about this, which is about heat flux. So heat flux is rate of heat transfer per unit area. And Q, capital Q, we'll use it for heat transfer rate. And in fluid mechanics, we have used this Q for volumetric flow rate. Yeah, don't confuse that Q and Q here. Wherein in your thermodynamics, you would use this Q for heat energy. That is heat energy in joule. சரிதானப்பா படிச்சிங்களாப்பா thermodynamics or in your basic mechanical engineering course? You would have used this capital Q for what is it? Amount of heat transfer, amount of heat that is to be supplied or to be removed. So whereas we are using this capital Q for heat transfer rate, or is whatever the Q, capital Q's you studied in your basic mechanical engineering or thermodynamics course, that is normally involving in only in terms of joules. Otherwise, your thermodynamics course, you won't study about this rate of any process. You will simply restrict yourself to the energy transfer. The rate of energy transfer is subject of discussion in this heat transfer. Okay, see, and okay, what is Q, small q and capital Q we have discussed, and capital A refers to the heat transfer area. Okay, heat transfer area and fluid mechanics area, how they are different and all we'll see later. So heat transfer area, this say in the case of a flat plate, the area of the plate, length and breadth. And in the case of a flow through a pipe, say assume you have a circular pipe and heat is traveling from the surface of the pipe to the inside of the fluid flowing inside the pipe. So in that case, the heat transfer area is going to be equal to pi by pi d into L. So it is called as pi dl. So pi d is the circumference. Phi d is the circumference of the cylindrical pipe. L is the length of the pipe. Otherwise, this entire surrounding area of the pipe is at a higher temperature, and heat is going inside the. It is traveling from the solid surface to the fluid inside the pipe. So otherwise, the heat transfer area is pi dl. Otherwise, nothing but the area of contact between the fluid and the solid. Whereas in your case of fluid mechanics area, or is the flow area, in that flow area is simply pi by 4 into d square. And here, and this area also we have used in the shear stress studies, or is the Newton's law of viscosity. Whatever the area there applicable is actually the surface area, which is in contact with the fluid and solid. So otherwise, normally this A will be flow cross-sectional area. Flow cross-sectional area for the pipe is simply pi by 4 into d square, or is pi r square. Whereas for heat transfer, this area is pi d into L. Because normally we will be interested in exchanging the heat from the fluid around the tube to the fluid inside the tube. So heat transfer is through the entire surface area of the tube, which is simply equal to pi d into L. Okay, otherwise this area has to be appropriate. So normally there will be a confusion which area to use, whether it is a flow cross-sectional area, or whether the circular area or the surface area. What is it? The lateral area. Okay, now or is this capital Q, small q A? This is very common for all the discussions, either heat transfer by conduction, convection, or radiation. Now we are going to see the formulas for conduction. So this formula is quite similar to that of Newton's law of viscosity. So what is how do we relate this? What is called this law is called as a Fourier's law. How do we relate this Fourier's law and Newton's law of viscosity? So what are all the common terminologies? Say dt by dx. So what is dt and dx? Dt refers to temperature difference and dx is the thickness. As like this dt by dx, we have dv by dy, always velocity change with respect to distance, velocity variation with respect to distance. There was the similar term for dt by dx. And instead of k, we had again k. So what is a similar term in Newton's law of viscosity? Instead of k, we have viscosity. So k is thermal conductivity, and mu we have used, that is for viscosity. Of course, this negative sign, why it is coming, and in Newton's law of viscosity also we will be having this negative sign, but I didn't say much about this negative. No need to worry. This is about simply the transfer is happening from higher to lesser. So otherwise dt by dx. So if you otherwise temperature is decreasing with respect to distance. So otherwise this dt by dx is actually negative. So otherwise if you draw the plot, or do I have that diagram? Otherwise dt by dx is negative. In what way? Because you have a negative slope. Say this TSI will be higher than the TSO. So you'll be having drop of heat, or a drop of temperature, or x is increasing whereas y is decreasing. So dt by dy, dt by dx is actually negative, and to compensate for that we have a negative sign. So otherwise the direction of heat transfer is from higher to lower. So normally what is this dt by dx we expect? Otherwise slope normally will expect to be a positive quantity, but here the slope is a negative because of the direction of heat transfer is like this, always from higher to lower. So since this dt by dx is negative, whereas we want to have this capital Q or rate of heat transfer to be a positive quantity, so you will have a negative sign prior to the dt by dx. So as like this negative here in Fourier's law, even in your Newton's law also will have a negative sign. Not only that, even Fick's law in mass transfer, that also we'll see in the 4th unit, that also have a negative sign. Okay, everywhere, always from higher to lower, the direction of transfer, either it is heat transfer or mass transfer or momentum transfer, everything is in the direction of decreasing what is it, temperature, or decreasing potential. So since this dt by dx or dt by dy, sorry, what is it, dv by dy or dc by dy, everything is in negative. So we have to counteract that, we have a negative. That's a significance of this negative. Okay. Okay, let us understand the variables now. So the proportion again, it's also involving k, a. Whereas in your fluid mechanics, you would not have anything as like a. Instead, what we have seen is actually tau. Tau is actually similar to your capital Q by A. So tau is shear stress. Here it is heat flux. So otherwise, you can always write these things in a similar way. Capital Q by A is similar to tau in your Newton's law of viscosity, and K is having similarity with viscosity, and dt by dx is having similarity with dv by dy. Or is dv by dy is nothing but simply called as momentum transfer, direction of or is velocity change with respect to distance. Here it is temperature change with respect to distance. Okay, we'll see this again in detail. Yeah, here again, if this area is, if this dt by dx is linear, then we can simply write this as delta t by L. Uh, but sometimes this dt by dx is not linear. So how to deal with that situation and all, you will study in your heat transfer course. Okay. Otherwise, this equation is simply q equal to minus k into dt, ka into dt by dx. And for dt by dx to be a linear one, otherwise temperature profile is always having a constant slope, then dt by dx can be written in terms of delta t by L. So delta T refers to the inlet and outlet temperatures, and L refers to the thickness of the wall. And minus signs already we have discussed. Okay. So, okay, now nice question. காலையில சாப்பிட்டீங்களான்னு தெரியாது, சாப்பிட்டீங்களா சாப்பிடலன்னு தெரியாது. At least I am showing you வடை. இல்லை பக்கத்தில் வடை இருந்தால் எடுத்து சாப்பிட்டுக்கோங்க நீங்கள். Yeah, the question is, at least your answer is available now. So better I will. Question is, எதுக்காக நடுவில் அந்த வடையில் ஒரு ஓட்டை போடுறாங்க? Any of you are aware of this answer? You can tell me now. மெதுவடை பார்த்துருப்பீங்களா? சாப்பிட்டுருப்பீங்கன்னு நினைக்கிறேன், எல்லாரும் சாப்பிட்டுருப்பீங்க. நிறைய பேர் இப்போ பக்கத்தில் கூட வடை வாங்கி சாப்பிட்டுட்டு இருப்பீங்க, நம்ம சொல்ல முடியாது. மெதுவடையில் I would have seen this hole. What's a role played by this hole? நானே மொனட்டான பேசிக்கிற தூக்கம் வந்துடும், எனக்கே தூக்கம் வந்துடும் போட்டுருக்கு, உங்களுக்கு கட்டாயம் தூக்கம் வந்துடும் காலையில் இருந்துச்சா கூட. இப்போ சிம்பிள் கொஸ்டின்ப்பா. கொஸ்டின் இஸ், வடையில் எதுக்காக ஓட்ட போட்டிருக்காங்க? அஃப்கோர்ஸ் அது வடை பேர் ஓட்ட வடை. எப்படிப்பா?
ஆயில் நிறைய உள்ள போகும்.
ஆயில் உள்ள போகணுமா? பட் மக்கள் ஆயில் நிறைய பேர் விரும்புறது இல்லையாப்பா வைத்திஸ்? ஆயில் இருந்தா கூட பேப்பரை வச்சு தொடச்சிட்டுலாம் சாப்பிட்றாங்க எல்லாரும்.
அப்படி
oil is also coming in contact, of course. What is the need for oil to come in contact? Yeah, related answer only, correct only. Actually,
for the dough to be cooked well.
Yeah, it's getting cooked well. Fine. Sivasanmugam, you are trying to say something.
No, sir, the same thing.
So
actually,
what?
As the size is bigger, it cannot get
correct.
ஒழுங்கு வேகாது, அதனால
கரெக்ட். ஸோ நல்லா வேக வைக்கிறதுக்காக நடுவில் ஒரு ஓட்டை போடுறோம். ஸோ அஃப்கோர்ஸ் இதே இது ஓட்டை ஏன் நம்ம அந்த பருப்போடையில் ஏன் போடலன்னு கேட்கலாம். அது போட்டீங்கன்னா உடஞ்சு போயிடும். இது வந்து நல்லா போடுற மாதிரி இருக்கு, ஆல்ரெடி பஞ்சு மாதிரி தான் இருக்கு இல்லையா? இங்கே போடுறதுனால என்ன ஆகுதுன்னா, we are trying to actually increasing the heat transfer area. So as already pointed out by Vaidis, and you are also able to say the reason. So otherwise, because of putting this central hole, இப்போ என்ன ஆகுதுன்னா, ஃப்ளாட்டாக இருக்கிறத விட இப்போ என்ன ஆகுது, யூ ஆர் கிரியேட்டிங் திஸ் எக்ஸ்ட்ரா ஏரியா. இன்னரில் இருக்கிற ஒரு சிலிண்ட்ரிக்கல் ஏரியா இருக்குது பார்த்தீங்களா? ஸோ திஸ் இஸ் எக்ஸ்ட்ரா ஏரியா அவைலபிள் ஃபார் ஹீட் ட்ரான்ஸ்ஃபர். ஸோ நம்ம கண்டக்ஷன் ஃபார்முலாவில் பார்த்தீங்கன்னா வரும், இதை பார்த்தீங்கன்னா ரேட் ஆஃப் ஹீட் ட்ரான்ஸ்ஃபர் இஸ் ப்ரொபோர்ஷனல் டு த ஏரியா அவைலபிள் ஃபார் ஹீட் ட்ரான்ஸ்ஃபர். ஸோ அதனால் என்ன பண்ணியிருக்கோம், ஏரியாவை ஜாஸ்தி பண்ணியிருக்கோம். உருண்டை மாதிரி உள்ள போட்டீங்கன்னா என்ன ஆகும்னா, இட் வில் டேக் லாங்கர் டைம் டு குக். இன்ஸ்டெட் இஃப் யூ புட் சம் ஹோல் பை சென்டரில் ஒரு ஹோல் போட்டு விட்டீங்கன்னா என்ன ஆகும், ஆட்டோமேட்டிக்லி குக்கிங் இஸ் ஃபாஸ்டர். குக்கிங் ஃபாஸ்டாக இருக்கிறதுக்கு காரணம் வந்து பிகாஸ் ஆஃப் இன்க்ரீஸ்ட் ஏரியா. Of course, you can also say this with a lot of other examples. Even flat போட்டால் கூட you will be getting some increased area instead of this bulky or ball போகிறதோட. Simply you can easily understand this rate of heat transfer is proportional to the increase in area. So area, we are trying to increase the area by putting this central hole. நம்ம people from other region also know this. மெதுவடை எல்லாரும் சாப்பிட்டுப்பாங்க, right? So central hole is leading to increasing the area available for. Otherwise, so whatever you see in the nature surrounding, you simply observe them and try to incorporate in your studies. அவ்வளோதான். ஸோ எல்லாருக்கான இப்போ பசி எடுக்க ஆரம்பிச்சுட்டு நினைக்கிறேன் வடையை பார்த்ததும். இட்ஸ் நேச்சுரல் நோ, whenever we see some food item, அவர் இது எல்லாமே நம்ம பசியெல்லாம் எடுக்க ஆரம்பிச்சிடும். ஸோ பசிச்சா கூட சாப்பிடுங்கப்பா, பரவாயில்ல. நம்ம லக்கிலி பிகாஸ் ஆஃப் ஆன்லைன் வி கேன் ஹேவ் ஆல் சார்ட் ஆஃப் திங். நோ, அப்படி சாப்பிட்டுக்கிட்டே கிளாஸ் கவனிக்கலாம், ஈவன் தூங்கிக்கிட்டு கூட கிளாஸ் கவனிக்கலாம், ஒன்றும் பிரச்சனை இல்லை. ஸோ இன்க்ரீசிங் த சர்ஃபேஸ் ஏரியா லீட்ஸ் டு இன்க்ரீசிங் த ரேட் ஆஃப் ஹீட் ட்ரான்ஸ்ஃபர். And what else we said? We also said about this thermal conductivity. And this thermal conductivity also, no? How do you say this instead of this steel part? If you have this copper bottom material, it will be having a faster heat transfer because of conduction is faster with increased conductivity of the material. Whereas பழைய குக்கிங்லாம் பார்த்தீங்கன்னா மட் பார்ட் will be taking a longer time. There is relatively it's having less thermal conductivity. So the connection I will also see about the range of thermal conductivity. So thermal conductivity, it's having a range, wider range, starting from 0.0001 watt per meter Kelvin. தெரியுது நினைக்கிறேன் இல்லையா? Unit is x-axis unit is watt per meter Kelvin. So why this unit is coming in watt per meter Kelvin, that we will see shortly. The insulating materials have very high, very low thermal conductivity, and pure metals have very high thermal conductivity. Pure metals and say iron order, again copper is having very high conductivity. In comparison, silver and gold will have much higher thermal conductivity. But we cannot afford to use, otherwise we are not we are not normally using this silver material. We are normally using this steel materials or ions. So copper will be relatively having higher thermal conductivity. Copper and even sometimes aluminum is also having higher conductivity than iron. I am not sure of that. Okay, it's not available here. And even you see this diamond, which is a crystalline carbon, which is having very high thermal conductivity. Otherwise, the idea of saying this is the as and when the conductivity is high with pure metals. Okay. Stainless steel are having lesser conductivity than iron because stainless steel is alloy. It's a mixture of materials. So predominantly chromium and nickel are there in stainless steel, whereas iron refers to the simply ferrous, Fe, with some amount of carbon. And insulating material and again in comparison to the solids, liquids are having lesser conductivity. Say for example, you can see in comparison to ice, liquid water is having lesser thermal conductivity. And again in comparison, steam will be having low thermal conductivity in comparison to water. And in comparison, you can also say like what is it, through vacuum there is no heat transfer happening by conduction. Otherwise, for heat transfer to happen, we need to have molecules to be closely surrounding. If the molecules are highly having a large, if the distance between two molecules are very large, then it will lead to reduced conductivity. So that's why this in the gases, the thermal conductivity of the material, gases have low thermal conductivity in comparison to liquids. And like that, liquids have low thermal conductivity in comparison to solid. And again in solid, pure metals are having high thermal conductivity. Okay, at least this idea alone, you please have that in mind. And unit of this thermal conductivity is watt per meter Kelvin. We'll come to that, how this is coming. So this unit, how to get the unit for K. So capital Q is rate of heat transfer, which is joules per second or watt. And this area and L refers to the thickness. So area by thickness refers to again meter, meter square per meter. And this delta T is having the units of degree Celsius or Kelvin. So we'll be having watt divided by meter Kelvin. Simple only, no? So the thermal conductivity of solid, material is having the units of watt per meter Kelvin. So simply based on this formula. So this formula is nothing great, simple only. This rate of heat transfer is proportional to the temperature difference and again inversely proportional to the thickness. So that's why if you have a very thin material, the rate of heat transfer will be more. So thickness material, you would have easily felt this heat to transfer fast. No, the very thin material means quick heat transfer. To avoid that, sometimes what you will have a thicker material thicker material. In addition, we'll also have lesser thermal conductivity. Service rate of heat transfer is proportional to the conductivity, inversely proportional to the thickness, directly proportional to the temperature difference. Service everything it's having direct proportion except this thickness. We can easily understand the effect of thickness. No? Having highly thick material, you have lesser rate of heat transfer. So this formula is easily understandable, and you can also get a unit for K. Simply rate of heat transfer by area by thickness, no? Or is a meter square per meter, so it will be having meter, and this delta T unit having the unit of Kelvin or degree Celsius. So watt per meter degree Celsius or watt per meter Kelvin. Of course, both are the same because 1 degree Celsius change and 1 Kelvin change are the same. Yeah. How do you say? Or is, if you raise the temperature of water from 25 to 26, it's equal to rising the temperature from 296, 298 to 299. Or is 273 plus 25 odd, say 298 to 299. So, or is 1 Kelvin rise or 1 degree Celsius rise. Both are the same. Whereas 1 degree Celsius and 1 Fahrenheit rise are different. That you know, no? It's about 1.8 times, no? You can easily relate that from the formula. Okay. So watt per meter Kelvin, it is a unit, and you know the significance of every variable. Okay. Similar to this thermal conductivity, there is another unit we'll normally use in heat transfer, which is normally to say about the capacity of material to store energy, what is called specific heat. So kilojoules per kg degree Celsius. In what way this Cp and K are similar? So this instead of power unit we have energy unit, and instead of distance we have mass. You can easily understand this specific heat, which is about the ability of material to store heat. Say for example, water needs about 4.184 joules to rise the temperature by 1 degree Celsius. Otherwise, it can store that much of heat. Say 4.184 joules, it can store. Of course, it is able to. In that thing, it's the temperature is rising by 1 degree Celsius. Say for example, this thing, no. Water is having normally this water is having very high thermal content. What is it? Very high specific heat power. Whereas the specific heat of water is very high in comparison to most of the other materials. The specific heat of water is 4.184. Whereas in terms of calorie, how much it is? 1 kilocalorie per kg degree Celsius. So one is now turning to 4.184 because of the conversion between calorie and joules. Say for iron, it is actually only 1/10 of this specific heat. With this related significance and all, you will understand more in your heat transfer course. Okay, let us not study much in that. So next thing is about convection. Another about 15 minutes available. So 15 minutes level right. And again, to remind you, I will upload this entire unit's recorded lectures. You please go through at your own pace. So for coming class, no, that is on Wednesday, we will try to see about that other topic as well. In addition to finishing this first topic, which is about the modes of heat transfer, we will also see about the temperature profile. At least for these two lectures, you please go through the video and come prepared for the coming class, so that we'll have more of discussion instead of myself presenting. Everyone try to make a discussion on the topic. So, okay, coming to the next topic, which is about convection, which is happening because of the movement of this visible movement of molecules. So always it is happening because of fluid moving over the solid. So assume the solid is at a higher or lesser temperature. So energy is going from the solid or coming from the fluid to the solid. Okay. And of course, you would have already come across with this equation Q equal to H into delta T. This is very similar to your conduction equation. In what way this is differing? Instead of what is it, dt by dx, we have simply only dt or delta t available. This x is absorbed with h. Otherwise, this h is actually dimensionally equal to k by the thickness. Since in the convection we cannot see this, what is otherwise the entire fluid is moving, so we cannot say about this thickness through which the conduction is fluid heat transfer is happening. So otherwise there is a bulk movement of fluid, so entire things are is the conductivity and otherwise conductivity is or is this, so this heat transfer coefficient depends on the conductivity of the material. 1 minute, there is some. Whereas this equation, Newton's law of cooling, is very similar to Fick's law of conduction. The difference is, of course, earlier there also we had A and delta T we had. Instead of H we had K. 1 minute. So otherwise, this H is dimensionally equal to K by thickness. Thickness is easily understandable in this conduction because there is a thickness of the solid object. Whereas here in this fluid, so what to say about the thickness? So there is no thickness as such is available here. Instead, we are grouping that inside the variable of H. Otherwise, H is nothing but a very interesting heat transfer property of the fluid. Otherwise, H depends on a lot of factors. So otherwise, simply to say, H is a function of thermal conductivity and a lot of other fluid properties. Say, it depends on the geometry of the heat transfer equipment and the velocity of the fluid, or is a fluid velocity, fluid property like the density, viscosity. So a lot of factors are going to affect this H. In addition, it is also depends affecting the it is also depending on the temperature difference between the solid and fluid. So this delta T is nothing but the surface temperature of the solid and fluid temperature, which is denoted with T infinity. T infinity bar. This is alpha. This is actually infinity symbol. Provided this temperature heat is traveling from solid to liquid, solid to fluid. Otherwise, if the travel is reverse, then T infinity minus Ts. Okay, you have that formula rearranged. So this cuts, whereas earlier we had only this nice property, thermal conductivity. Thermal conductivity is what is called as a transport property, as like viscosity of a fluid. Transport property means the property value whenever it's applicable for this fluid in motion or heat in motion. So otherwise, what is it? The thermal conductivity. Otherwise, heat in motion is nothing but the heat transfer. So this H is what is simply called as a heat transfer coefficient. H depends on a lot of variables. Predominantly, it is a function of capital K. K is thermal conductivity. The thermal conductivity is small k. K. In addition, it depends on the heat transfer geometry, equipment geometry, and fluid velocity, fluid density, fluid viscosity, even fluid. What else? We also sometimes it's also a function of specific heat and density difference, temperature difference available. Okay. Yeah, this simple law you would have already come across in the name, what is called as Newton's law of cooling. It's not only Newton's law of cooling, it is also Newton's law of heating also you can take. Simply Newton's law of heat transfer. Okay, now heat transfer by convection, we can again classify into two types. One is what is called as forced convection. say forced convection means you assume there is a contents. You are forcing this heat transfer to happen by means of putting a stirrer by agitating this content by the way of simply by stirring in the with a glass rod in the case of a small capacity, or by having agitator driven by a motor. You can have a flow. Otherwise, you can even have a flow by forcing this fluid to pass through some heating coil or cooling coil or a jacket. So what is called in these cases, the rate of heat transfer is happening by what is called as forced convection. Otherwise, the convection is forced by means of stirrer, fan, pump, compressor, or whatever means. Whereas in natural convection, we don't have this kind of setup as like a stirrer or a pump or any other thing. Instead, heat transfer is there is a flow created because of the density difference, as what is happening in your cooking vessels. நம்ம மேகி போட்டுக்கு முன்னால தெரியும் இல்லையா, மேகி போட்டு காமிச்சிடலாமா? சி காலையில் வடை பார்த்தாச்சு, அடுத்து மேகி. These are all the easiest வடை போடுறதோட மேகி போடுறது ஈஸி. How do we start this process? You take some contents. Normally we won't put this Maggi packet அப்படியே போட மாட்டோம். We'll take water and allow it to get heated up, and as and when it starts boiling, we'll put the content. If you do that way, then your cooking will be fast. Otherwise, it will take a little longer time. அதாவது மேகி சமைக்கிறது கூட ஒரு மெத்தட் இருக்கு. மேகி சமைக்கிறதுக்கு என்ன பண்ணும், டேக் திஸ் கண்டென்ட் சர்வீஸ் என்ன எடுக்க போறீங்க, சிம்பிளி யூ டேக் எனஃப் வாட்டர் அண்ட் ஹீட் த வாட்டர், and once the boiling is initiated, then you take this put this Maggi contents, Maggi any noodles, then you will be easily getting this noodle will be getting cooked in that time of say 2 minutes. People used to say 2 minutes. Once it started getting boiling, otherwise boiled water போட்டீங்கன்னா 2 minutes கிடைக்கும் சான்ஸ் இருக்கு. This even Maggi also I used to say, some 20 years back, like during our college days, I have seen this for the first time during my hostel only. Upon 90, in the period of 90, 90 May. I just joined in 1990 June. காலேஜில் ஜாயின் பண்ணால் அப்போ தான் அந்த மேகிங்கிறதெல்லாம் பார்த்தோம். அப்போலாம் ஈவன் யூஸ் டு ஹேட் திஸ் மேகி ஆல்சோ. நூடுல்ஸ் டு சிம்பிளி சேல் நூடுல்ஸ் வித்வுட் சேயிங் எனி பிராண்ட். இட் வாஸ் லைக் சிமிலர் டு அவர் நம்ம சேமியா மாதிரி இருக்கும் இல்லையா. சேமியா வி ஹவ் ஆல்ரெடி சீன், பட் ஸ்டில் we haven't get adjusted to this taste, and always we haven't started liking this taste. After about some 1 or 2 months time, it was tasting better always in comparison to நம்ம சேமியாவோட அது நல்லா இருக்கும். So we started taking that. Otherwise, I could see this Maggi there in the market for more than 30 years. Correct தானப்பா? Even it was banned for some time, ஒரு 3-4 years back இல்லையா. பட் அதுக்கப்புறமும் மார்க்கெட்டில் வர ஆரம்பிச்சிச்சு. People are saying like the reason for this taste is because of some components what is called as MSG, monosodium glutamate. There is some taste enhancer. Some sort of chemicals are there. Okay, better not to take this very often. சரிதானப்பா மேகி சாப்பிடுறது? ஓகே, பசிக்க ஆரம்பிச்சுன்னு நினைக்கிறேன். Even I will also stop this class. We will stop this with this free and forced convection. So you can easily say that the forced convection heat transfer will be much faster, whereas free convection, it is also called as natural convection. It is happening naturally because of the hot object. So as and when you started heating, the fluid which is closer to the layer will be at high temperature, and this high temperature fluid will tend to rise up because high temperature fluid is having low density. Okay, this low density fluid definitely will go up because the high density fluid will be coming down. So there is a natural circulation created. This is because of the temperature difference. The temperature difference is leading to density difference. The density difference is leading to the circulation. So these circulations are very fast whenever this boiling is happening. That's why we wait till this boiling is happening. So once the boiling is initiated, then of course it will continue. So we are normally waiting for this boiling to start. Even this is the procedure for even cooking the rice also. No, say those who are cooking rice with this pot, what they will do, they will take the water and allow this and heat the contents. And once the boiling is initiated, then only they will pour this rice. Not only this, even upma சமைக்கிறது கூட அப்படிதான் இல்லையா? Any of you know how to cook upma? Rice, everyone, of course, everyone of you know Maggi cooking. There is by default, I can take it for granted. And rice cooking, some of you may be knowing. Upma cooking, I don't know, many of you may not be knowing also. Because you won't like this upma and all, no? Because these are all like very olden food, no? Old age foods. சாப்பிடுறீங்களாப்பா உப்புமாலாம் சாப்பிடுறீங்களாப்பா?
Yes, sir.
Oh, Gautam is taking upma, rice. Upma is also like Maggi மாதிரி தான். That also will get cooked in some 5 minutes time. சமைச்சு பாத்தீங்களாப்பா? You know how to cook upma?
Sir, no, sir. But mother only will do.
Mother only will do. You can also learn that. It's very easy. Whereas rice cooking may take some 15-20 minutes time. Whereas in open pot it may take some more time. Whereas in cooker it will take some 10 minutes minimum. Whereas upma கொஞ்சம் குயிக்கா பண்ணிடலாம்ப்பா. Maybe girls-லாம் நிறைய girls 3 months தெரியல. Nowadays these girls are boys are more always doing cooking quite commonly than girls. Even I can say from my house also, I can say like at least whenever anything is needed, I can easily cook. Whereas if my house is having a lot of ladies, then they will definitely order the contents. Now idhirla Swiggy, Zomato illa irukanga illaya, they are delivering. Whereas I am comfortable with simple rice and curd. Okay, I should not say about my thing. It's common, predominantly common. Okay, we'll continue from this aspect in the coming class. To quickly summarize, conduction and convection we have seen so far. This rate of heat transfer is proportional to the area available for heat transfer. That's why we are having this hole in the meduvada, and also we will have this, what is it, any pan with bigger surface area, bigger bottom. There we are having higher heat transfer area, and also thin material will have lesser they will have faster rate of heat transfer, and you know the effect of conductivity and everything. Okay, we'll continue from this aspect, and we'll see in the coming Wednesday. Before that, you please go through these video lectures that will be posted shortly. Okay, see you all in the next class. Another about about 3 students are missing. So no problem, we'll take this attendance for granted. Or a simple exercise. All of you please log out from this Zoom and go to this LMS and log out. LMS page, you can log into LMS PCE Principles of Chemical Engineering course and log out from there. Simply if you log in and log out, I can understand who class how can I come to know? I can based on your last access to course. This based on attendance. Okay. Otherwise, the requirement is you please log into LMS and log out from LMS. Okay. See you all on Wednesday.
Thank you, sir.
Yes. Thank you.
Thank you, sir.
Thank you.
Thank
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, Pa.
Thank you.
Thank you, Ambika.
Thank you, sir.
Vanakkam, Pa.
Thank you, sir.
Thank you. See you all. And I need to Amarnath. One of the students hasn't submitted this test paper. Any of you haven't submitted this test paper, please do that. I haven't.
Thank you, sir.
Thank you, Mark. Thank you, Sandhya. And I haven't received one of the paper. No, I will let you know. Sarath Kumar, yeah, Sarath Kumar. Sarath Kumar, Sarath Kumar.
நான் சப்மிட் பண்ணிட்டேன் சார்.
இது எனக்கு வரல. ஒன்னு பண்ணுங்க, அந்த PDF இருந்துச்சுன்னா எனக்கு மெயில் பண்ணிடுறீங்களா?
ஓகே சார்.
Mail you can simply Subramanian M மெயில் ஐடி தெரியுமா உங்களுக்கு?
ஓகே தெரியும் சார்.
Yeah, then simply mail that. ஏன்னா இதுக்கு ஒன் சேரல அப்படின்னு தெரியல. சரத்குமார், தேங்க்யூப்பா. தேங்க்யூ. See you.
தேங்க்யூ சார்.
தேங்க்யூப்பா வைதீஷ்.
தேங்க்யூ சார்.
கௌதம், தேங்க்யூ. பார்க்கலாம். க்ளோஸ் பண்ணிடலாமா? ஐஸ்வர்யா, you are available?
Yes, sir.
Thank you.